Hello and welcome back to Calculus 2, section 10.6 on alternating series. So this is number 8, I believe, on our list, and we'll take care of the last two tomorrow. Now, alternating series are very easy to spot because they all have this negative 1 to the n times an. They can start anywhere, can start at 0, at 1, so I'm not going to write anything. Now, it's not just negative 1 to the n. You can have negative 1 to the n. You can have negative 1 to the n plus 1, negative 1 to the n minus 1. And you can also have these trigonometric ones. You can have cosine of n pi. See, cosine n pi would give you also the same situation, because if n is 0, cosine of 0 is 1. And then when n turns to 1, you have cosine of pi, and that's minus 1. And then cosine of 2 pi is 1 again. So cosine n pi is the sneaky way to try and hide alternating series. And then you have obviously one with a sine with n pi over 2, which does the same thing. So these are all different forms that you can have alternation. So it's not just negative 1 to the n, but most of the time it's just negative 1 to the n. So it's very easy to pick these out of the bunch. And what they have is a kind of tree path that I would like to call from the start of the problem all the way down to the conclusion. And here is the path. For alternating series, you look at first, you look at the limit, you look at an. That's what you look. So you take away the sum, you take away minus 1 to the n, and you just look at an. Now, if an is decreasing and the limit an is 0, as n goes to infinity. So if these two conditions are met, you are already on a convergence branch. And on the convergence branch, now you are going to look at the summation of an. Again, no minus 1. And then that one either converges or diverges, which leads into what we call absolute convergence or conditional convergence. I'll explain all of this from scratch. Let me just spell it out. Absolute convergence, conditional convergence. So you guys have now two different types of convergent, and I'll explain that. On the other side, if the limit n goes to infinity of an is different than 0, you have divergence. So alternating series converge absolutely, converge conditionally, or diverge. And they're the only ones that do this. Everyone else has converge or diverge. This messes up your odds in guessing 50-50. But such is life. Yeah, go on a test and you just say converge for all, right? You're pretty much guaranteed to hit half of them, right? And then there's your 50 out of 100, right? If you know nothing on the test. It doesn't work that way. But anyway.
No, we gotta write the sentence. We look like we know.
Write the sentence.
The same sentence.
I'm gonna read that sentence, man, so I'll know. All right.
Write it really small. So all you see is the C of the circle of a sentence.
Yeah, I'm not. Yeah, zero is so much more, so much less effort, right, to write than -5, let's say. Anyway, so we start with the AN sequence, and we make sure it's decreasing, and we make sure that the limit is 0. If those two conditions are okay, then we take a look at the summation of that AN sequence, and that can be any of the other tests. P-series, comparison, whatever, integral, anything. And now that one is going to converge or diverge. But look, you are already on a convergence branch. So if I am to cut this in half, right, you have convergence to the left and divergence to the right. So even though this diverged, it's still in a convergence region. And I have an excellent example to explain this confusing part here. If the limit is different than 0, it diverges. You can use the limit test. You can use anything else to show. So this is like your roadmap. Start the problem, and then one of the 3 conclusions on the bottom. So let's take a look at few examples. Summation of -1/3 to the n, from 1 to infinity. Well, we're going to massage this little bit with algebra and write this as a summation of -1 to the n, and then 1/3 to the n, 1 to infinity. So this is how you know that it's alternating series, because you see it, right? It's right there. What you do is you pick off AN as 1/3 to the n. You know that the graph of that one are going to be these dots, because this is like the exponential 3 to the -x, right? Which goes like that. So you know it's decreasing. You can also take the derivatives and whatever else to show. And you also take the limit of 1/3 to the n, and you will get 0. So both conditions are fulfilled, which means you hopped onto convergence branch. So you started with AN, and then you went into, now you have to do summation of AN. So you already know that it's not divergence because both conditions are satisfied, right? You have a check mark and a check mark on 2 conditions. You are on a convergence branch. So the next step now is to compute summation of AN. But hey, that's summation of 1/3 to the n. What do we know about this puppy? Geometric, very good. And it converges because r is 1/3 less than 1. Geometric series. If you're still having trouble, guys, I gave you the sheet of paper, right? You have it right there on second row. Converges if the r is smaller than 1. We have 1/3. So now you are on a convergence side, which leads to absolute convergence. So answer, since AN is decreasing and limit n goes to infinity of AN equals to 0, and summation AN converges series, summation -1/3 to the n absolutely converges. or converges absolutely. AC. Converges absolutely. Whatever. AC is what we are looking for. You are on a convergence branch, then the summation of AN converged as well. So 2 convergence in a row leads to absolute convergence. Next example. Summation of -1 to the n times 1 over n from 1 to infinity. Alternating harmonic series. Nice, huh? What do we know about harmonic series? Diverges by either P series or integral test. How about alternating? Well, let's check. AN is 1 over n. Is it decreasing? Yeah. And what's happening with the limit as n goes to infinity of 1 over n? Zero. It's on a convergence branch. Way to make things really confusing, huh? Okay. So we started with AN. Both of these conditions checked out, and now I have summation of AN to worry about. So we know it's not divergence. Looks like this is going to converge. Holy nightmare. What's the summation of 1 over n now? Well, we already said it, right? It's harmonic series, diverges by integral test, let's say. So it's on the divergent branch here, which goes to conditional convergence. So we say since 1 over n is decreasing and limit n goes to infinity of 1 over n equals 0, and summation 1 over n diverges, the series summation -1 to the n over n conditionally converges, or converges conditionally. Now, I really like this, and I love the wording, because the test shows that alternating series converge conditionally. So it's like there is a condition under which it converges and condition under which it will not converge. And that condition is exactly the alternation, the -1 to the n piece. Look, to sum up this stuff, let's do blue. Summation of 1 over n diverges. Summation of -1 to the n over n converges conditionally. So what's the condition for it to converge? Condition is to have that alternating part in it. You remove that condition, it becomes harmonic and becomes divergent right away. Absolute convergence is equivalent to convergence that you guys had for all other tests. So we can actually just say absolute convergent for all of them, but there is no need, because alternating series are the only ones that have conditional convergence and absolute convergence. All others converge absolute. So it's converge or diverge, and that converge is absolute converge. For alternating series, you have this mid-step with the conditional convergence, and the conditional convergence, again, is happening sometimes, not all the time. Sometimes, and we just saw the best example possible, which is alternating harmonic series, where when the condition is in, it converges, you remove that condition, it diverges. It's a very nice thing. Let's take a look at, one or two more from homework. By the way, that's it. You need to know the path that you take from the start of the problem to the end of the problem. You strip off the summation, take off also the -1 to the which is alternating term, and you're just left with the sequence AN. That sequence needs to be decreasing, needs to be in a limit 0, and you are on a convergence branch for the series. Then you do the summation of AN, again, no alternating part. That one will converge or diverge, leading you into one of the two types of convergence. Going back to the original sequence, if the sequence in a limit is different than 0, then the series becomes. Now, this branch over here, guys, this is your divergence test, right? Look at your sheet, the first row. That's it. So, divergence test helps there immediately to see that divergence. Let's take a look at another example. Problem 14. Summation 1 to infinity, -1 to the n, 1 plus 1 over n to the n. Great. You immediately start with an is equal to 1 plus 1 over n to the n. We don't have to go immediately with decreasing. Let's try the limit first in this case. What's the limit of this? This is a famous limit that you should know by heart without solving. It's a basic calculus definition. Equals to what? This is technically equivalent to calculus of you writing your name on SAT. Definition for not E. E. Some of you went no, E. Definition for E. Box this thing. Not 0, diverges, boom, done. Problem solved. No, I did not. I'm going to forfeit 2 points on this problem as the instructor. Now, however, you get to write the sentence, obviously, because life is not fair. That's the best explanation. Exactly. Wait out of your college to see that. I can give you 5,000 examples off top of my head. So if you are able to spot that an part is not going to go to 0, do that limit first. As soon as that's not 0, it immediately goes on the divergent and you are done. So, decreasing part, you should do second, right? Because if it fails on the limit, it's divergent, you're done. So you just wasted your time working on decreasing first. Do the decreasing second. Something else nice. How about 24? And we're done for the day. Summation 2 to infinity of -1 to the n divided by n ln squared n. All right? We know what to do. An is equal to 1 over n ln squared n. Now, for a situation like this, where all of the variables are in the denominator, and you just have 1 on top, it's immediately obvious that decreasing is a pass, and limit an equals 0 is a pass. That's immediately obvious because the higher the n goes, you can't have negative numbers for n. So the higher the n, the smaller the number, right? If you go 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, right? So as the numerator increases, because n has to grow, the values decrease for the full, so decreasing is immediately obvious. And then the limit, obviously, 1 divided by infinity is going to be 0. So we already know this is on a convergence branch. Now, is it conditional or absolute? Is going to be summation of 1 over n ln squared n. And now the question is, which test do we use to solve this? What do you think? What test? No, integral test. You can integrate this. If your ln is u, then you have 1 over n for du, so you have 1 over u squared, right? Integral test. Is it continuous? Is it decreasing? Is it positive? 3 conditions. Then the integral test. Then, right, all of that stuff. So after an hour, you finally find that it's convergent and you have absolute convergence for the whole problem. Question is, can you compare this to 1 over n squared? Maybe. Maybe. So, integral test. Is it continuous? Yes. Done. Why is it continuous? Because polynomials and ln are continuous on 2 to infinity. That's what we have. 2 to infinity is our domain. because the summation starts at 2. So we are only care about polynomials and ln function, right? Both continuous on this. Quotient is continuous since n cannot be 0 because, again, 2 to infinity. We are on that domain. So now we proved that it's continuous. Is it positive? The answer is yes, again, because 1 is positive, n is positive for n being 2 to infinity, and ln n is squared, which is always positive. So when we combine all these positive numbers with multiplication, division, and so on, we get positive. And finally, decreasing. Well, yes, you can use the same argument, 1 divided by increasing numbers gives you a decreasing number. So 1 divided by increasing numbers gives, increasing sequence. That's one. Increasing sequence gives decreasing sequence. That's 1 over 2, 1 over 3, 1 over 4, 1 over 5, whatever they are. So now that all conditions are satisfied, we can integrate 2 to infinity, 1 over x ln x squared dx, u equals ln x, du equals 1 over x dx. So we have limit b goes to infinity, 2 to b. It's not going to be 2 to b. It's going to be ln b and ln 2 because we have to plug in the limits. We get 1 over u squared du. That's going to be limit b goes to infinity of ln 2, ln b. We'll go back. Oh, no integral. I'm integrating now. It's u to the minus 1 over minus 1 from ln 2 to ln b. Now go back to x values so we can use negative 1 over ln x from 2 to b, which is limit b goes to infinity of negative 1 over ln b, minus and minus gives me plus 1 over ln 2. ln of infinity is infinity, 1 over infinity is 0. So I get 1 over ln 2. Converges. So what do I have? I have a convergence branch, and I have a convergent value there. So answer. Since an is decreasing and limit an is equal to 0, and summation an 2 to infinity converges, we saw by integral test, the series summation 1 over n ln squared n converges absolutely, so absolute convergence. Ta-da! That's it. We'll finish the last 2 tests tomorrow. And from that point on, you'll have the stuff. They'll have all 10 tests. Bye.
And so what are we